Okay, so let's go ahead and talk about the overall time complexity of Dijkstra's algorithm and some of the challenges to using it, and then we'll look at an overview of a proof of why it works, why it's correct. Okay, so first of all, let's do a quick review. So we're going to be using a priority queue here to access items. So that'll kind of indicate our idea of getting the minimum valued item. So we used the binary heap earlier in the semester. It was pretty good at many things. If you remember, it was kind of a better balance between being able to do inserts and removes than the alternatives we looked at. So in this case, we'll be adding and removing each of our vertices. So it kind of makes sense that we would use a binary heap. Okay, so the insert and extract min operations in our particular binary heap were logarithmic operations in terms of the number of items in the heap. There was one other operation we supported on our actual implementation. We had a dynamic priority queue, which we really need here. As we're going through that process of relaxation, we're changing the priorities of things. So we need to be able to decrease the overall value that's stored in the heap. So we need to use the decreaser object. Okay, so if you remember, that actually kind of required the idea of the bubble up or the heap up operation, which was also logarithmic in terms of the number of. Okay, we also need to use a graph here, so we have to reconsider graph implementations. Really, one of the key points of Dijkstra's algorithm is that we need to be able to traverse to adjacent vertices quickly. So if you remember, once we get extract a particular vertex as our next one to consider, we'll need to look at all of its outgoing edges. So hopefully that suggests to you the idea of an adjacency list. That was one of the operations it was really good at. Okay, so with that, let's go ahead and analyze the overall pseudocode that we had to work with earlier. So the pseudocode requires processing each vertex. So this also has some implications on our graph implementation. We're going to assume that our graph implementation somehow has an efficient list of vertices, that we can iterate through the vertices in a total of the number of vertices time. So for example, if we have 50 vertices, we're going to assume that this loop has a complexity of 50. Okay, there's some other details here that we have to make some assumptions about. I'm going to assume that marking a vertex as finished or unfinished is a constant time operation. It'd be easy to add a particular property to each vertex to do that, or we could use some auxiliary data structure that's efficient, like a hash map, for instance. So if we either include the distance in the vertex itself, or again, if we use the trick of some auxiliary data structure like a hash map or even an array, if each of our vertices can be numbered, then the marking of the distances and initialization is also constant time. Okay, the thing that's a little bit different here that we do have to consider a little more carefully is this insert operation. So it's going to insert something into a priority queue. So this is basically building our priority queue. We're going to assume that the insert is a logarithmic operation, although there are ways to build our initial priority queue a little bit faster. Just for the time being, I'm going to assume that this is log base 2 number of vertices. We'll see that with the rest of the algorithm, it actually turns out that that even if we were able to do this particular part a little bit more efficiently, we're still going to have this factor of log 2 of the number of vertices involved. Okay, so all of this in total, we could kind of summarize to be number of vertices, our loop, times log base 2 of the number of vertices. Okay, so that's kind of our initialization. Let's go ahead and look at the actual heart of the algorithm here. So again, there's a loop that's going to loop over all vertices, and we're going to assume that it's going to loop based on the number of vertices we have, so that'll be kind of a multiplier there. Now we have to kind of scrutinize each thing that goes on in here. So I'm going to go ahead and work these out with that multiplier involved. So we've got the extract min operation, so the loop will cause that to execute for each vertex. And the extract min operation is log base 2 of the number of things that are in our loop, of the number of things that are in our priority queue. The next line of code is a for loop. So remember, we're using an adjacency list, so when we're at a particular vertex v, we'll be able to iterate through this relatively quickly. So this loop will basically iterate the number of, for each outgoing edge from a particular vertex. And it will happen for every vertex in our graph. So in total, this will represent the number of total outgoing edges over the entire course of the algorithm. So we could think of this entire loop as not being affected by this outside loop, but being affected by the total number of edges we have. If it's an undirected graph, it'll be twice this. If it's a directed graph, it'll just be based on outgoing edges. Okay, so this if statement at most is going to execute once, execute for every edge, either once for a directed graph or twice for an undirected graph. Okay, and then inside of here we have our update of distance, and this is going to be retrieving an edge and doing some math. If we have direct access to our vertices here, this will all be relatively efficient. I'm going to assume all of that's a constant time operation. But this decrease operation is where things get a little bit ugly. So this is dependent on the number of items in our priority queue. So again, this is, if you remember, it's going to be log 2 of the number of things we have in our queue. Okay, so I'm going to go ahead and redraw that. And remember, it's going to execute for each individual edge in our graph. So, okay, if we combine together these two things, we'll have our total amount of time. I'm also going to assume that marking things as finished is constant time. So we'll end up with number of vertices plus number of edges times log 2 of number of vertices as our overall total time complexity for this particular implementation. And remember, the initialization was also v times log base 2 of v. So when we convert things to the big O notation, that we would just have that occurring twice. So we'd drop the constant, and we'd end up with this total overall time complexity. Okay, so our overall time complexity, if we use an adjacency list and a binary heap for our priority queue, is broken down into these two parts. The initialization part, which depends on the number of vertices, and for each vertex we have to do an insert into our priority queue, potentially. And then the actual loop part. And for the loop part, we have to extract each vertex from our priority queue. So the number of vertices times the amount of time it takes to extract a single one. And for each of our edges in our entire graph, we may have to do an update of priorities in the priority queue. So for number of edges we have times the amount of time it takes to change a priority in our dynamic priority queue. So if we combine together these two parts, it turns out that the first part is kind of subsumed by the second part. So we, even if we could do that more efficiently, it's not particularly critical. So we can kind of simplify the time complexity to just being a factor of the total number of vertices plus the total number of edges times log 2 of the number of vertices. Okay, so there are also some limitations we need to consider with Dijkstra's algorithm. So as we already saw when we looked at the Wikipedia article, it indicated that negative weights aren't supported. So let's look at two cases where negative weights would cause Dijkstra's algorithm to find an incorrect solution. So the first case is where there's a loop. So in this case, if we start at our start node S, we have a cost of 5 to get to vertex 1. And then we've got a cost of negative 5 to get to vertex 2, followed by a cost of 1. So initially, we'd kind of assume that the distance from S to 1 is 5. But it turns out that we've got this loop here where we can end up subtracting 4 by going from our start to node 1 to 2, and then back to node 1. So we start with a path cost of 5, and if we go through this loop once, we end up with 5 minus 4, a path cost of 1. And if we keep circulating around this loop over and over and over again, our path cost keeps going down and down and down. So this is one of our potential problems. So when we've got a negative sum in loops, there's really no minimum possible. We could go around in the loop an infinite number of times and continually decrease our overall cost. Okay, so let's look at a slightly different problem that doesn't necessarily have a loop. So again, we'll consider negative weights. If we have non-increasing totals, it's also a potential problem. So this graph doesn't have any loops, but it does have two ways we can get to node D from our start node S. So Dijkstra's algorithm would start by taking the outgoing edge with the lowest cost, which would take us to B. We would process all of the outgoing edges from B, and then our total cost going out of B to D would be 2, versus the other path to C would have a total cost of 3. So next we would expand node D, and we would check it off as being completed. Even though if we would traversed a slightly different path, we'd end up having the outgoing value of 3 plus an outgoing value of 2, ending with a total of 1. So because of the order in which we'll process nodes, we would come up with an estimate of 2, but if we'd been able to process them in a different order, we'd be able to end up with a total cost of 1. Okay, so this is just kind of a assumption that Dijkstra's algorithm works under. It works under the assumption that paths will only increase or stay the same, so that there are no paths that actually end up decreasing as we go through additional links. And that's what's happened here, and that's why Dijkstra's algorithm won't work for this particular scenario. So to be assured that Dijkstra's algorithm will find shortest paths, we have to have graphs with non-negative weights, so 0 or greater on all of our weights. Okay, so let's walk through a proof of correctness of Dijkstra's algorithm. So we're going to assume that edge weights are non-negative, so they're 0 or greater. And we're going to start with a claim that we'll try and prove. The basic claim is that by the time we get to a vertex V in that while loop and extract it from our priority queue, at that point, V's perfect correct distance is already known. So we've already identified the minimum distance to get to that node. So by the time that inner for loop executes that goes through all the edges out of V, V's distance is the minimum distance to V from the start node. So we're also going to introduce some notation here. So we'll think of the function D as giving the actual true minimum distance between two nodes. So we'll almost always be thinking about this in terms of the start to some vertex V, but there'll be like one other example too where we consider it between two vertices. Okay, so just like most of our proofs, we'll do a proof by induction. So remember that induction is kind of about associating elements with the natural number line in some way. In this case, we'll think about the order in which we go through the vertices as we remove them from the priority queue. So that will be the sequence that we're progressing through. And our base case, of course, will be the start node. So the start node is explored first. Its distance has to be 0. Edge weights are greater than or equal to 0, so it couldn't possibly be any less than 0. And just by convention, by our initialization, we'll set its distance to 0. Okay, so by the time we explore the start node, its correct true distance is known. Okay, so now let's focus on the induction part of it as we get to vertices 1, 2, 3 after our start node. So our induction hypothesis, we're basically relying on strong induction here, that all of the preceding vertices already do have correct perfect distances known by the time we get to vertex K. So when we get to vertex K, every other vertex in our sequence that comes before K, as we're removing things from the priority queue, its v.distance is already perfect. Okay, so let's assume we're exploring a vertex V, and by the time we get to it, its distance is actually greater than the true perfect distance. That is, that there's some better path than what we found so far. So this is a contradiction to our induction hypothesis. So our hypothesis is that all the preceding nodes already have perfect distances. We're going to assume that the next node we get to has an incorrect distance. And it's important that we're considering it to be greater than the true distance. So we'll use that in just a minute. So if we can demonstrate that this is in fact a contradiction, that it can't be true, if our estimated distance isn't greater than the true distance, then it has to be equal to the true distance. Because remember, we're relaxing it closer and closer to the true distance. And we start off with a really, really pessimistic estimate. So we won't ever be able to go below the true optimal distance. Okay, so let's consider the true shortest path to our hypothetical node V. So we've got our V node out here somewhere. We've got our start. And we meander through various nodes, and eventually we get to V. We want to focus on the other nodes that this may go through. So we're going to put an intermediate node here, and I'm going to label that as U. And we've kind of got two different cases of U. So we could have this where U is immediately adjacent to V on the shortest path. That's one option. Option number two is where there's other intervening stuff here. So we'll consider these two cases. We'll also consider U to be the last finished node. So that means that we already know U's optimal distance. Okay, so U is the last finished node, so we know its perfect ideal distance. And we also know that the distance from the start to U has got to be less than or equal to the distance from the start to V, since U is before V on its shortest path. So again, we go from the start, meandering along to our node U, meandering along to our node V. Okay, so we've already got this distance to U, and the overall distance to V has to be greater than or equal to that, because the individual edge weight of this intervening stuff, the total sum of those edge weights in between, has to be greater than or equal to 0. Okay, so we'll consider this in two different cases. So case number one is if there's an edge directly from U to V on the shortest path. Okay, so what I mean by that is we've got our start, meanders to U, and then there's an edge directly to V, and this path through that edge is on our shortest path. So when we explore U and expand its edges, we'll basically go ahead and update V to be the sum of the distance to U plus that edge weight, which would be its perfect distance. So that would be the correct value of the distance all the way to V. So that contradicts our assumption. So this first case contradicts our assumption that V's distance would be greater than the actual optimal distance. So if there's an immediate connection here on the optimal path, then V must already have its correct true optimal distance, because its value would have already been updated to that when we processed U. So let's consider case number two, where there might be some intervening nodes after U. Okay, so case number two, there's some uncompleted vertex V in between the two. So start, meanders along to U, and immediately after that there's X, and then some path that eventually goes to V. Okay. So in this particular case, we know that the total distance from the start to X will have to be less than or equal to the distance from the start to V. Okay. So this intervening stuff here will have to be have a total sum of links of 0 or more. Okay. Okay, since V does not have its correct path distance, remember that was our assumption, we know that the actual distance estimate in V must be greater than the distance estimate in X. So remember, The distance estimates are relaxing, getting closer and closer to their actual true estimate. And our original assumption that we're trying to prove is incorrect is that V's distance is still higher than its actual true value. And we've just said that x will be, the distance to x will be less than or equal to the true distance to V. So the distance to x must be less than this estimate, this pessimistic estimate of V. And that means that x would have had a higher priority. We would have had to have explored x before V. It couldn't be unclosed. So we've again got a second contradiction. So in this case, we would have had to have already processed x. So either we already processed u and V got its correct estimate, or we've got this unknown intervening node x, and we also would have had to have already processed it. So we've got kind of two contradictions here. So our original assumption that V's distance was incorrect must be incorrect. V must have the correct distance by the time we get to processing it, by removing it from the queue and processing it in the loop.